Are you familiar with this chapter? Magnetic effects of electric current. Did you did you ever hear this phrase? Yes. If you are 10th standard, so of course you will be familiar with this. It was it will be it would be taught where in 8th standard or 9th standard or 7th standard. Okay. Uh, in this lecture, we will start from basic, from a scratch, from a scratch till the advance. We will start with the meaning of this phrase, and then it will be continued. We have started, and now in front of you, there is a slide. In this slide, it is saying magnetic. This magnetic effect of electric current. It is the name of this lecture. Now, what topics are we going to cover? Are this all those topics are here, which are mentioned here. We will learn about basic properties of magnets. We will learn the relationship between electricity and magnetism, magnetic field and magnetic field due to a current through a state conductor. Then we will see right hand thumb rules. Then we will see magnetic field due to a current through a circular loop. Then we will have magnetic field due to a current in a solenoid. All these topics will be discussed with you, and I will be instructor. You can say educator. I will be educator. Shall we start? Are you comfortable? Do you have any doubts? If you have, then you can use a comment method. This medium. This medium is useful. I'm not saying useless. You have to use. If you have any type of doubts, then you can comment me. And here, but doubts should be related to this lecture. Now I am going to start it. We are starting with the introduction of magnets. Okay, what is a magnet? You know. If you don't know, then don't worry. I am here to explain it. What are magnets? What are magnets? Electricity and magnets. All these topics will be discussed. These are topics. So here now we have started. This is magnet. This is also magnet. This is also magnet. This is also magnet. All these are magnets, and work of all these magnets are same. And what is the work of all this work? You will realize, don't worry. Right now, I said that work of all these objects, all these magnets are same. Now I can directly say that work of this magnet is to attract or repel the magnetic materials. Magnetic material should be conductor. Should be conductor. Do you understand work of this magnets? If yes, then okay. If no, then I would like to repeat it again. Work of all these magnets. I'm not saying work of iron. I'm not saying work of magnetic material. No, I'm saying work of this magnet is to repel or attract the iron materials. Clear? It is a device which attracts iron materials, which repel the magnetic material, the magnets. These are magnets. Okay, here magnet. Here you can see there is a letter which is S, and there is another letter which is N. Remember, S stands for south and N stands for north. This is pole and this is another pole. We have two poles in this magnet. We are breaking down it. This is magnet, and a magnet will have two poles. One pole would be south and second pole would be north. Remember this. Now here This is animation you can see. What is happening over here? Yeah, this magnet attract this tongue made of uh, iron you can. So this magnet power you can see power of magnet. It attracts. It behaves like electricity. As we put magnetic materials near to the magnet, then it will attract very high. Yes, very high. You can see. Yeah, this magnet is attracting conductor material. If you are putting insulator material near to the magnet, then it will not work. It will not work. Okay. Now here, iron nail, yes, magnet will attract this, but this is a insulator. It will not attract because it does not have electron. That's why ions. So clothes. This will not magnet will not attract this. Even electricity, this will not conduct electricity. So this part magnet will attract this part, but not this part, because this part is made of a plastic. It is a insulator. Now here we have what will happen in this. This will be attracted, this will be attracted, but this part behind this part will not be attracted by this magnet. RNL magnetic materials, these are magnetic materials. We are saying this and this is magnetic materials. Magnetic materials are materials which will be attracted by magnet. Any material you are taking, if those materials are being attracted by magnet, so those materials will be called as magnetic materials. Any material you can take. I have what this. I have this. Inside this there is a magnet, but there is a magnet here. I think so. Oh, this is a tape. This tape is a what? It is an insulator. With proof, can we say that this is insulator? Yes. Just you will have to put this material in front of a magnet. Then one case, if this is not being attracted by magnet, then we can say this is insulator. This is one proof. You are putting a magnet. And you have also a material which is insulator. You put that material in front of a magnet, but that magnet didn't attract this insulator. It means this does not have something you will see. Right now you understood that magnetic materials will be attracted by magnet. That's it. Here, this magnet will not attract this. This magnet also will not attract this, because of these are insulators. This materials does not have electrons or ions. You can say ions, non-magnetic materials. So this will be known as non-magnetic materials. Okay, we are crystal clear. Now here we have different shapes of magnets, different shapes of magnet. This is a U-shaped magnet. This is a bar magnet. It is called as a bar magnet. And this is a ring circle. And it is a horseshoe magnet. It looks like a shoe of horse. That's why it was named as horseshoe magnet. These are different shapes of magnet, but work of this will be same, not a different. Okay, here this is bar magnet. Okay, here in this we have 2 poles. First is north, second is south. Bar magnet will look like a rectangle. This is north pole and this is south pole. Yeah, we are crystal clear. Here, what will happen in this case? This is south and this is south. both are in front of to each other, and both poles are south same. In that case, both will repel to each other. Both will repel to each other. Rather than attracting to each other, both will repel to each other because of both signs, both poles are same. As we are familiar with science, that if both the signs are different, then both will attract to each other. But both are same, then in that case, both will repel to each other. Clear? Same here you can say. Both are not being attracted to each other because of both signs, both hints are same. That's why. Like poles repel each other. Yeah, okay, now. In this case, what will happen? Here we are observing this. In this, we have north and here both in front of to each other. One is a north pole and second is a south pole. In that case, what will happen? In that case, both will be attracted. The reason is that different hints. There are different hints in front of to each other. In front of each other, there are different poles in front of to each other. Here you can see both magnets are attracting to each other because of unlike poles. That's all. Now next, a bar magnet has a two poles. Yes, all magnet has a two. I think so. North pole, south pole. We have seen. Like poles repel each other. Yes, and unlike will not repel to each other. Rather, it will attract to each other. Okay, this is done. Now next, electricity and magnetism. What are magnets? We are clear about it, and we are we are continuing on this. Electricity and magnetism. What is happening over here? You are not able to see. Magnetic compass. This ship will find direction. How? Just by using this. If they want to go in north direction, they will use this. By using this device will tell you that this side is north, this side is east, this side is west, this side is south. So this compass will tell you exact direction. It was made like a device, and it is working as a device. So the name of this is what? Magnetic compass. Here we are adding magnetic word with the compass because inside this you will perhaps you will see magnet inside this. That's why it is working like that. Okay. This is a device. It is used to find a direction. Okay. Work of this device is to tell direction. We can use it according to requirement. Now here, as you can see, here this part is a magnetic needle. This part is magnetic needle. Here over here, what is happening? Magnetic needle. This one side will tell about north and this side will be south. Now in this case, both are same. This is north and this is south. This is north. This is north and this is south. It's a magnetic needle and it's a bar magnet. Okay. Now this is north seeking pole, and this would be south seeking pole, and this would be east seeking pole, and this would be west seeking pole. Here you can see. Now voltage. This is a device. By using this device, as we know that we can find what electrical potential difference is by using this voltage device. And here we have current. This current. It is also device. Here you can see this V and this A. It is an ammeter. It is used to find electric current, and this is used to find voltage, clear voltage. Same here. This magnet is used to this magnet is also this is a device. It is used to find direction as in needles detects a magnetic effect. Magnetic. Same here. This is also a device. Here it is telling you that this side is north, this side is south. This is telling you. Here what is happening? This bar graph, bar magnet and this you are using. What is happening? It is not attracting this. This is not attracting this because both poles are same. That's why. Name of this person is Hans Christian or Orsted. Orsted. Current carrying wire behaves. Current carrying wire. This wire carrying this current wire carrying wire behaves like a magnet. What I am saying? I am saying current when carries wire, then it will behave like a magnet. Yes. Inside this there would be magnetic field. Let's visualize this by this. What is happening over here? We have this. This is a compass needle. This is a conductor, cell, millimeter, plug. Okay. Here what will happen? It is going like that. This is a conductor and it is a wire. This is cell. When it will be, then it will find electric current. Again this, again this. Conductor. This is a conductor, and here we have magnetic compass. Okay, we know current follow. When it is switched, when this is switched, then current starts flowing, isn't it? Here we have magnetic needle deflection. When switch will be on, then this will start behaving. Magnetic needle deflection. Here we can see it is working. It is working because there is a connection of electricity with this. That's why it is working. What is it? Electricity and magnetism are related to each other. Yes, there is some connection of electricity with magnetism. There are some connection. We cannot ignore it yet. Electricity and magnetism are related to each other. Let's see how is it related to each other. A magnetic compass needle is a small bar magnet. A magnetic compass needle is a small bar magnet. Needle, compass needle is like a bar magnet. The end of needle pointing towards the north is called north sinking or north pole. The end of the needle point towards the south will be called as south seeking or south pole. Yeah, we now this a current carrying conductor, a current, a current carrying conductor inside the conductor. A current is a flowing. So a current carrying conductor behaves like a magnet. Of course, it will behave like a magnet. The magnetic needle gets deflected. The magnetic needle gets deflected when brought near a current carrying conductor. If electricity is passing just close to the magnet, then it will work. Magnet will work. Magnet will start working. When current is passing just close to the magnet, then magnetic field and field lines. We are done with this. Now we have this bar magnet. Yeah, and what else? So let's see. This wall will be magnetic field. I can say how. In this field, both will work. It will be attracted by this because this is not magnet. It is a needle. What happening? What happening in this? Here there are more distance, and here mass of this less, and this is also less. So that's why. In that case, distance should be more, not less. Okay, distance should be less. Then both will attract to each other. But in this case, mass of this is more, and mass of this is also more, and distance is the same. Distance is the same. So in this case, we are observing that both are being attracted to each other because of mass of the object. Force of attraction. Force of attraction. This is it is attracting this magnetic material. So this will be known as magnetic force. This will be known as magnet. A magnet is attracting a magnetic material. So this is also force, but this is a type of a force, and this type of a force is a magnetic force. So what is the definition of a magnetic force? A magnet which is attracting a magnetic material will be a force, and this force is a magnetic force. That's it. Now towards it we have this. What is happening over here? As we put a object both near to each other, then both attracts. But distance is more, then both will not attract. So distance matters here. Here, magnetic field, invisible field. This is what invisible field. Here, what else can be observed here? So a place where both stars are attracting, that place will be magnetic field. Here we can see this is invisible. We cannot say directly this visual this field where this magnet will work. This is invisible field, and around this here on magnetic field, if you put any magnetic material, then magnetic material will be attracted by this. When you will put this that magnetic material uh, around the magnetic field, then but it is far away from the magnetic field, then magnetic material will not be attracted. Okay. Now invisible field, yes, you can see this is here in magnetic field. This magnetic material is in magnetic field. That's why it this attracted this. So sheet of a paper, we have this sheet of a paper, and on this sheet of a paper we have this bar magnet. What will happen here? Let's see. uh, iron fillings, pieces of iron we took, and put we put around the this around this bar magnet. What is happening here? You can see what is happening. It is showing that it is showing about the magnetic field. This is where is a magnetic field. Here, if you put any magnetic material, then this will attract. So this wall will be what magnetic field. Here you can see this wall is magnetic field. This specific pattern is what magnetic field. This specific pattern is a magnetic field. If you put another magnetic field here, the distance is more, then that magnetic material will not be attracted by this. Okay. So it looks like that. This is pattern of magnetic field. This is pattern of a magnetic field. Okay. Magnetic field lines. Oh, these lines. It is talking about this line. So pattern of a magnetic field lines is like this. It is going like that, then like that. From north to south. And here we can see south, and it is here in this. It is coming out. North to south. What is happening? North to south. We have this component. What happened? Nothing. North pole, south pole. Yeah, we know this is north pole, this is south. This is what? South pole, north pole. Then what will happen? Nothing. Yeah. And this is a maze of this. This is a diagram of this. Yeah. This would be what? Here we can see. What is that? Oh. What is happening here? Here you can see. As we move like that, a compass here, both are attracting to each other because both are different. And here, same, here we will get both are different. So this is a diagram. So here we can see north to south will attract to each other. If you take the same north, then both will repel to each other. So here it is telling you that here both are different because both are attracted to each other. Okay, and as it comes like that, then it attracts both to each other. Here we have north south, here we will have north south, south north. This is a figure of a magnetic field lines. This figure from north to south, again like that. Same process. This is how magnetic field works. This is how. These are magnetic field lines. Okay. The reason surrounding a magnet in which the forces of the magnet can be detected is said to have a magnetic field. Yeah, It is saying that this is magnetic field. This is a place where magnetic field is appearing. These lines which represent the magnetic field are called magnetic field lines. Yes, we know. Properties of a magnetic field lines. What are those properties? Let's see. First, it will start from north to south. It will start from north to south, like that, like that. Yeah, north to south. This is the first properties. And second is, what is happening? This is second. Here one. Okay. Direction of a magnetic field at A. Yes, this is a direction at A. Okay. A, B, C, like that. It is a direction of a magnetic line. Magnetic field lines do not intersect each other. Yeah, we can see any line are not any lines are not intersecting to each other. You cannot see. You will not be able to see intersection of magnetic field lines. Yes, this is the third property. You will not realize like that. Not possible. Two direction of magnetic field at a single point. No, both points will be alone. Will be traveling alone. Magnetic field lines emerge from north pole and merge at a south pole inside the magnet. The direction of magnetic field lines is from south to north pole. Thus, magnetic field lines are closed curves. The relative strength of the magnetic field is shown by the degree of closeness of a field lines. Therefore, magnetic field is stronger at the poles of a magnet. Yeah, here we can see this and this. They are stronger. Completely, they are stronger because here it is attracting very high. This is also attracting very high. At which of the following points strength of magnetic field is maximum? So this N and S. No. See why? Because all these are coming like that. So and also these are coming here. All these are coming out. Next, magnetic field. Magnetic field due to a current through a straight conductor. We are going to take a conductor which will be a straight, and we will apply current inside a conductor. Then we will see magnetic field. With the help of a conductor, and when we will apply current inside the conductor, then can we see magnetic field? Let's see. Here we came to this magnetic field due to current in a state. Okay, we are familiar with this, but we don't have a conductor right now. Only we have a magnet. Now we have this compass, and this is wire. You can say this is wire. In this wire, electrons are working. That's why we are saying this current is carrying this. This current is carrying this. This current is carrying this conductor. And here we have this magnet. We have this magnet. What is happening? You can see. We can see this is working. This is working. It works when it is near to this. When it is near to this electrons, and it starts working. Because as we know, both are linked to each other. Electricity also behaves like a magnet, and magnet behaves like electricity. Both are opposite to each other. Here pattern, shape, copper wire, current. Okay, this. This is in a state. This is in a state. When compass will be applied, when magnet will be applied, then you can say something will happen. Okay, cardboard, iron fillings, here iron fillings, okay, around this wire, iron fillings. What is happening? This is a pattern. This is pattern. Magnetic field lines. When iron fillings are put surrounding the conductor and inside the conductor current is passing, then this pattern will be shown. Will be shown like that. This is a pattern of magnetic field around the current carrying conductor. Both are different. Here we are using only magnet, but in this case we are using a conductor which is conducting electricity, and both are making different magnetic field. In this case you can see gradually it is becoming, radius is becoming more large, you can see. So strong field is where? Here at center, and at outside would be weak field. Weak field. At center is a strong field. Less deflection. Here more deflection. Why? When it is near to this, then there would be more deflection. Work of this would be more, but it is a far away to this, then this needle will work less, you can see, because here we have weak field. Here we have weak field, but here we have a strong field. Current, it is going like that. This is current, you know. Now what is happening? Deflection increases. Current increases. When current will increase, of course, this deflection will increase. And if this is near to this conductor, then this work of this needle will increase when current will be increased. Current decrease, deflection. If this if this is at a certain distance, but current is increasing, current is being increased, then of course deflection will decrease automatically. This magnet is depend on current, not conductor. Magnet is depend on current, not conductor. In this context, I am saying magnetic field at a point increases or decreases when current flowing in a conductor increase or decrease. Yes, when current will decrease or increase, then magnetic field also will decrease or increase. Magnetic field. The magnetic field lines are in the form of a concentric circles. Yes. For a straight current carrying conductor, the magnetic field produced by a straight current carrying. Okay, this is for you. This is also for you. This is pattern of a magnetic field of a magnet. You know, right hand thumb rule. What does it say? What does it mean? Let's see. Let's explore. Right hand. We are going to use right hand, not left hand. It can be there in this lecture, but right now we are going to explore what is the right hand thumb rule. This is a rule, and that is a fixed. This is rule, we cannot manipulate this. So conductor, we took a conductor like that, we hold a conductor like that, like that. This is what is a right hand thumb, right hand. Here we can see. Current is passing through this, current is working, okay, electrons are working, and we hold this. Now what is happening? Surrounding this magnet field, there is a magnet field surrounding this, it is working. We can feel less current at this moment, less current. Direction of a magnetic field is like that. This is the direction of magnetic field when we hold a rod, then this is a pattern of magnetic field. Current upwards, current is going upward, anti-clockwise magnetic field. Right hand thumb rule. Imagine if you are holding a current carrying wire in your right hand such that thumb points in the direction. This thumb will indicate direction of a current, in the direction of a current. Then the fingers will curl in the direction. This finger will tell you that this is the direction of a magnetic field. Here you can see this fingers is telling you direction of a magnetic field, and this thumb is the direction of about direction of current. This current is going in this direction, and magnetic fields are working in this direction like that. So all this can be found out how, just by using this right hand thumb rule. With the help of this thumb, we can say this thumb will tell about the direction of a current, and these fingers, end of these fingers will tell you direction of a magnetic field. Clear? That's it. A current is flowing in a straight wire in a downward direction. What will be the direction of magnetic field around the conductor? Here we saw that current is going in this direction. But what if current is going downward? Then what will be direction of this? I think it should it be positive? Let's see. Should it be opposite, not positive? In that case, what will happen? By using right hand thumb rule, the direction of magnetic field will be in clockwise direction. We are still using right hand, but now we hold like that. Here direction of a current is in this, and this will be what? Clockwise. In the previous, this was anti-clockwise. It will be just opposite. This is like that. It will go like that. This magnetic field direction will be like that, and this current direction is a downward. If a current direction is a downward, then this magnetic field direction will be like that. If we are holding like that a wire which is conducting electricity, in that case this thumb is about, it is telling you that this is the direction of a current, and this fingers is a direction of a magnetic field. Okay, clear? I hope you are clear. Magnetic field due to a current through a circular loop. Hold on. This is I'm not familiar with this, but I can explain it. Don't worry. Straight conductor. Yeah, straight conductor. This is This is a state conductor. If we have a state conductor, then pattern of magnetic field will be like that, like a circle, concentric circles. Activity, current loop. This is state, but now this is like that. Circular loop, circular. Here, okay, yeah. Then circular loop. Here, both. Wow, wow. Hmm. Mm-hmm. Magnetic field lines. Yes, yes. Concentric circles. Yes, concentric circles. This is conductor, but it is a circular conductor. This is a circular conductor. In that case, what is happening? Here, both are coming to each other, isn't it? Both ends are coming to each other. That's why they did work. Right hand thumb rule, you know. Here, what is the direction? Like that. This would be direction of a current, but this would be direction of a magnetic field, anti-clockwise, and this would be clockwise. Yes, both are coming to each other, both are coming together. That's why this worked. Current increases, magnetic field increases. When current will increase, of course, magnetic field increase. Magnetic field will increase. If magnetic field increasing, it means current is increasing. Now, magnetic field lines for a circular loop are in the form of a concentric circles. At the center of a loop, magnetic field lines become straight. Right hand thumb rule is used to find the direction of a magnetic field. This is for you. If the current in the wire increases, the magnitude of the magnetic field at a point also will increase. Okay. If the current inside the wire will increase, then magnetic field around that wire will increase. If we increase the number of turns in the wire, the magnetic field will also increase. Number of wire. Magnetic field due to a current in a solenoid. What is a solenoid? We are at last topic. This is a solenoid. Here you can see it. It is a conductor. We are going to use this with this. We will see something. Don't worry. This is conductor. When we will apply current in this, then what will happen? Copper wire. Oh, yeah, I know copper wire. It was in a straight direction, but now it became circular loop. Copper wire wrapped around a cylindrical object. This is wire which is wrapped by this object. What will be magnetic field, magnetic effect? Solenoid. This is what solenoid. Name of this is a solenoid. Okay. Magnetic field lines. It will work like that. This will be pattern of magnetic field, and here you can see. Now, what is it? This is the same as we saw here. Both are same. Patterns are same. North pole here, south pole. Okay. Parallel magnetic field lines. Yeah, these are parallels. Uniform magnetic field. Yeah. Electromagnet. soft iron. We have soft iron, and we wrapped a wire by this object. Then we used this seal here. We used this rather than using bulb. Now in this case, what will happen? It will gain. This will gain magnetic field. That's it. This will gain magnetic field. That's it. It will behave. This needle will behave like electricity. What is happening here? These electrons are working, and this wire is wrapped by this. This object will work as a magnetic, as a magnet. This is what is an electromagnet. Soft iron. A coil of many circular turns of inserted copper wire wrapped closely in the shape of a cylinder is called a solenoid. This shape will be solenoid. The pattern of magnetic field lines of a solenoid is similar to bar magnet. Yeah. Magnetic field lines inside the solenoid is a parallel inside the, we saw here in this here, it is talking about inside the solenoid is a parallel. This indicates the magnetic field is uniform inside solenoid. A strong magnetic field produced inside a solenoid can be used to magnetize a piece of magnetic material such as soft iron. When placed inside the coil, the magnet so formed is called an electromagnet. The magnetic field inside a long state solenoid carrying current is zero. Wow. The magnetic field inside a long state solenoid carrying current is zero. Decrease as we move towards its end. Increase as we move towards its end. Is the same at all points. Here answer is the same at all the points. This is a question. The magnetic field inside a long state solenoid carrying current is zero or this. So all the points will be same. Is the same at all points. Now here, next question we have. So all this is for you. We will learn about the force on a current carrying conductor in a magnetic field, Fleming left hand rule, electric motor. All this will be talked. Force on a current carrying conductor in magnetic field. Let's see. Force due to magnetic field. Fleming left hand electric. Magnetic field around a current carrying conductor. Magnetic field pattern looks like that. When current is going, if a current is going upward, then it will start, this magnetic field pattern will start moving like that. Force on magnet by current carrying conductor. What is happening over here? Here it is giving more force to this. Is it happening? Yes, both are giving force to each other because both has force. It has magnetic force, it has electric force, I can say, and both are giving to each other force. Both are giving force to each other. Clear? Are you crystal clear? activity. Here we have this activity. It is very amazing. Aluminium rod, where this is aluminium rod. Aluminium rod, and it is what? Magnet. Now what is happening? Here this is a connected like that, like that, like that, and like that. Then again, then again. What is happening over here? But this is, you can say, here is we have a battery, and here is a what? Switch. You can consider it as a switch. Now when this switch will be on, then this will start working. This is also connected to this. Now this will hit on this surface when switch will be on, because this will attract. Here we have aluminum rod, this will hit here, it will come to like that. Here we have battery. Now here what is happening? As we know, this will go like that, like that, like that, then it then again like that. Horseshoe magnet. South pole, north pole, yes, we know. Then we have current follows from B to A, B to A, like that, B to A, not A to B, B to A, B to A, like that. This is working because of a magnet, because of a magnet. Here you can see this is wire, brother, this is wire, and here we have battery, this is a switch. Now switch is on. Okay, switch is on. Now what is happening? This is working, and here it is this is going B to A, B to A. Rod displaced towards right. When switch is on, then this rod is placed right. Why? Current carrying conductor experiences a force when placed in a magnetic field. Here this is attracting this, this is attracting this. That's why if the current will be more, then it will this will attract this more. The direction of forces, the direction of forces gets reversed when direction of current is reversed. Here what is happening? Just opposite, no, not opposite, north to south. That is the nature of north to south. Then this will, wow, here you can see it is a placing towards the right. Why? Because this is the opposite. We have converted this into like that. Force on current carrying conductor, direction of current, okay, direction of magnetic field, okay, both will be at 90 degree. Fleming's left hand rule, this, what is it? Fleming left hand rule, let's see. It is like that, this, and this is, it will come like, so here this will come like that. Here it is aluminum rod, it is working like that. And this is what? This is a force, I think it should be force. No, this is not force. This thumb is force. This is a current, okay. What else? This is magnetic field. Yes, this is magnetic, this is current, this is magnetic field. So here middle figure, and this forefinger, and this a thumb. What is the work of this magnetic field? It is a magnetic field. Yeah, this is a magnetic field. Okay, and this is a current. Okay, and this is what? This is a force. This is force. Here attraction is happening. Conductor. Of course, what will be the direction of a force? This is a direction. This is the direction of a force. Here this will attract to this, of course, because as we know, north is attracted by south. North is attracted by south. South will attract this north. So direction would be what? Like that. This is the direction of a force.